Now let us imagine a right circular cylinder in the liquid with the line CD as the axis and the point C and D are at the centers of the surfaces. Okay, surface of the cylinder. Now let us consider the liquid inside the cylinder, which is in equilibrium under the action of forces exerted by the liquid outside this cylinder. These forces will be perpendicular to the surface of the cylinder everywhere. Okay, so actually the force is because of the liquid present outside the cylinder. The force is on the cylinder, so the force here is towards this direction, and here the force here is towards in this direction. And if you see, both the forces are perpendicular, okay, perpendicular to the surfaces on which they are acting. Similarly, if you see this surface, again it is perpendicular to the surface. Okay, the force because of this liquid on this imaginary cylinder is perpendicular to the surface. Now it is also clear that if you take F1 and F2, the forces on the flat surfaces C and D, okay, that is the point. Now let us see an application of Pascal's law. So according to Pascal's law, if pressure is changed in some part of the liquid, then this change is transmitted equally to all parts of the liquid. So this fact is used in the hydraulic lift. Okay, hydraulic lift, hydraulic brake, hydraulic press, many other devices. Now let us see about the hydraulic lift. So yes, it is used to lift heavy loads, okay, such as cars, and in service stations we use. It is based on the simple principle, okay, that is when a small force is applied over a piston of smaller cross-sectional area, then because of transmission of pressure, a larger force appear over the piston of larger cross-sectional area, and this force is used to support the heavy weights. Basically, if you see a hydraulic lift, it consists of two cylinders of cross-sectional area A1 and A2. So if you take A2, it is larger than, very larger than A1, and it is connected by a horizontal pipe. And each cylinder is fitted with the airtight frictionless piston. The cylinders are filled with incompressible liquid. Suppose F1 is the force applied on the piston of smaller area of cross-section A1, then the pressure exerted over the liquid is, so that pressure is equals to P, or I will write here, P equals to F1 by A1. This pressure will be transmitted to the unchanged piston of larger cross-sectional area A2. Therefore, the upward force F2 exerted on the larger piston, that is given by F2 equals to P into A2. So what is the value of P? That is F1 by A1, and it is here, it is A2. So F2 equals to F1 by A1 into A2, and since A2 is very larger than A1, the force F2 will also be very greater than F1. So the heavy load placed on the larger piston is easily lifted up. So from this I can write F1 by A1 equals to F2 by A2. Effect of gravity on fluid pressure. So the Pascal's law in its original form does not take into the account of gravity, but this expression P2 is equals to P1 plus H rho g, that is what we have written, P2 minus P1 is equals to H rho g. From that I have written P2 equals to P1 plus H rho g, indicates the pressure varies with the depth height, and this is the modification of Pascal's law. Now you can see the following points are with regarding this. The liquid pressure is same at all points at the same depth. So if you take at this depth, then the liquid pressure, the pressure is same at all the points at this depth. The liquid pressure at a depth h below the surface is greater than the atmospheric pressure. So if suppose this is here there will be an atmospheric pressure, and if you see here what is the pressure at this point, in addition to the atmospheric pressure, another pressure, that is rho hg, that will also be there. So at a certain depth h below the liquid surface, the pressure will always be greater than the atmospheric pressure, that is P naught, that is atmospheric pressure, plus some value of pressure, that is rho GH. Okay, that is here I have mentioned the P naught is atmospheric pressure. The pressure at the bottom of the container does not depend upon the shape or size of the container. Whatever may be the shape or size of the container, it does not depend upon it. The pressure at a certain at a depth in a liquid depends only upon the density of the liquid and depth h below the free surface of the liquid. So we have told the pressure at the bottom is not dependent upon the shape or size, but it is dependent upon the density of the liquid and depth h below the free surface of the liquid. Here we can see three vessels of different shapes, but they are filled with the same liquid up to same height. Then we also find the pressures at the bottom of all the three vessels is same as shown by the pressure meters. Okay, although the quantity of liquid in different vessels is different, the height is same. The height of the liquid level is same from the free surface, and the density of the liquid is same everywhere. So the pressure is equal in all three cases at the bottom of this cylinder or at the bottom of this vessels.